Professor Roald Hoffmann is Polish-American theoretical chemist and Nobel Laureate in Chemistry at a young age of 44. After surviving a struggled childhood in labor camps in Poland during war, he came to USA in 1949 and studied bachelor's in chemistry at Columbia University and master's and PhD from Harvard University. His PhD work was under the joint supervision of Martin Gauterman and William Lipscomb, who himself was a Nobel Prize winner in chemistry in the year 1976. Since 1965, he has been working at Cornell University. Professor Hoffman received a Nobel Prize in Chemistry in 1981 for his theories concerning the course of chemical reactions. He has published more than 450 scientific articles. Curiously enough, this great scientist's publications include well-known collection of poetry, plays, and essays that reflect his personal philosophy on mutual influence of arts and science and the ways scientists should think. Roald Hoffmann is indeed a tireless advocate of the wonders of science and the beauty of chemistry.
I'm very happy to be talking to you from very, very far away, made possible by the wonders of technology. I want to tell you a story about chemistry, not about my own research at all, but just about a certain view of chemistry, actually 3 views that you will see. And there in the title, it says essential tensions. And one wonders what those tensions are. And perhaps by the end of the seminar, I will have made that a little bit clearer. What I want to do is to give you 3 views of chemistry which are not your typical view of chemistry. Your typical view of chemistry focuses quite naturally on chemicals, their influence on us, which is often beneficial and sometimes harmful. It focuses on the special features of chemistry, which will emerge along the way. But I'm more interested in how chemistry here fits into culture, broadly defined. And this will become clearer as I go along. So let me begin. The first is to come to a definition. So actually, there are going to be 3 definitions, which are in back of the 3 views. And the first definition, which has been there for a very long time, is that chemistry is the art, craft, and business before it became a science of macroscopic substances and their transformations, their changes, so that the canonical equation, A plus B going to C plus D, is not a bad symbol for what chemistry is, what chemistry really is. Now, it always was a business, and it was a business because it was useful. It was a craft because people worked at it. Let me give you an example just to focus that what I've just said. So here are 2 artistic representations commissioned in different places in the ancient world. At right is the Gate of Ishtar. These are actually enameled bricks, and the bricks are colored a beautiful blue, and it once stood in Baghdad, but now is, through a result of European imperialism, now in Europe, the Gate of Ishtar in Baghdad. At left is one of the great wall paintings from Ayanta. And you see here, it's a rather complex figure, and it has not been preserved terribly well, though it's a miracle that we have this. And in these, there is a blue pigment that's used throughout. Blue was very desirable in world culture. And the blue pigments here are of very different origin in these two paintings. And first of all, in the one at Ayanta, the blue pigment is something called ultramarine, which is powdered lapis lazuli, which was not common in the area of where the paintings were done, but actually is the product of trade with Afghanistan, not too far away. So the blue pigment is a powdered mineral. At right, the blue pigment is not a natural product. It is a product of commerce and manufacture and chemistry from 2,500 years ago, traded widely in the world of the Middle East, and a pigment called Egyptian blue. It came from the Egyptians' mastery of glassmaking, and essentially it is a powdered glass into which a blue pigment was incorporated. The blue pigment, the color, source of the color is a copper mineral, and the blue pigment source was either malachite or azurite, a mineral also, but it went through a manufacture in which it was made into a glass and then powdered and sold. We actually know the structure of the cuprate silicate that is that Egyptian blue. What is interesting to me is that these things were there, that sometimes they are natural, sometimes they are synthetic. Now, let's look a little bit more at this definition of chemistry as substances and their transformations. Here is an example. Here are two substances. They actually were not available pure till about the first decade of the 19th century. And they are aluminum at right and bromine. So they are actually elements. Bromine is this beautiful and not very healthy liquid with a reddish brown gas above it. One of these is placed into the other, and what you see is what happens here. That is copious fumes, flames, a small explosion, foul odors. In a sense, absolutely everything you expected of chemistry. And at the end of it is something which doesn't look like the aluminum, doesn't look like the bromine. It's an aluminum bromide that's actually a complex chemical compound. But there before your eyes is the transformation, A plus B going to C plus D. This transformation, of which this is just an example, is emblematic, typical of chemistry. And so are some other things that are shown at bottom here, which are crystals, here of copper sulfate, solutions that are colorful, sometimes crystals that are colorful, not all, most crystals are dirty white solids of one type or another. But these happen to be some compounds of vanadium. And these things are the colors, the crystals, the stinks and the bangs are to this day what attracts young people to chemistry. And in some ways becomes emblematic or typical of chemistry. It's very interesting to see that be maintained as an attractive element. Now, chemistry also happens on a much slower scale in every living thing. Here, for instance, is something which you will recognize better than I can, Nilan Kurinji from Kerala, and which I think there was a bloom 2 years ago, and you're going to have to wait, if you didn't see it, another 10 years to see this. But these beautiful flowers, in them is going on thousands of chemical reactions. And one of the joys of our current era is we know the chemical reactions that go on in these flowers. And chemistry proceeds there just as well, but it's not the stinks and bangs that attract young people to chemistry. Given that the changes are often as dramatic as you see them, and since this is a science all about change, whether the change is quick as in that aluminum plus bromine reaction, or slow in that, as in that flower that you can see only once every 12 years. But because the changes that are dramatic are often explosive, it has a consequence for how people think about chemistry, how they think about chemistry and see it psychologically. And that is actually going to be the third of the ways that I want to talk to you about. But to illustrate that another way, I'll show you something else. This is, let's see, I went the wrong way. This is the cover of a 1942 Donald Duck Adventures comic book. For the young people who don't know what comic books are, let me explain what they are. They are a prehistoric version of manga. So they were little books with lots of pictures in them which tell a story. Okay, so here is the story. The story in Donald Duck comic books, which were the most popular comic books in the time of 80 years ago, is very typical. Donald Duck comes in when his nephews, the three young people, are doing an experiment. They're doing a chemical experiment. He does something stupid. There is an explosion. Incidentally, no one is wearing safety glasses. This would not happen today. No one is wearing safety glasses. There comes something upon the head of Donald Duck, and that's supposed to be funny there, and it is in a kind of slapstick comedy funny, and that is the point of there is no point. This is the story of the comic book. It's just for fun. Now, an interesting thing is I wanted to show you the next panel enlarged in that comic book. It says, if I mix CH2 with NH4 and boil the atoms in osmotic fog, I should get speckled nitrogen. And the nephews, so Donald Duck is saying nonsense. And the nephews say he's talking chemical talk, but he knows nothing about chemicals. That's absolutely right. And it's interesting that the experiment that he describes in his nonsense way of mixing CH2 with NH4 is an experiment that has not been tried to this day. So Donald Duck is suggesting a scientific experiment. Now, if you are a chemist, you can think about why this experiment has not been done. And you can think about how easy it is to make CH2 and NH4 to start this reaction. I put it here just for fun. The part of the reason I also put this Donald Duck comic book, remember why I showed you this? I showed you because the Donald Duck comic book reflects circa 1942, but still today, one picture that people have about chemistry. Let me summarize it by a sentence. Chemists are the people who make things go bang. That's nice, but it's also pretty silly, and it does not take seriously the science. First of all, explosions are the best way in the world to waste all the product of a chemical reaction. You will not run a business based on explosions. And a chemical laboratory tries to avoid explosions at every cost, whether it is an oil refinery, as you see here at right, or a modern laboratory where someone is trying to make some pharmaceutical. Things are done cleanly and neatly and are still transformed, A plus B going to C plus D, but are done without explosions at all. But the explosions make better pictures, so they are there. So now we've had one picture, very briefly, of chemistry that I've given to you. And it's there to this day, that it's things and things changing. That's the essence. Now, since that time, in the last 200 years, through the efforts of men and women carefully at work, another kind of view of the substances transforming has taken place. And this is a microscopic view. This is a view that on the level of atoms and molecules that are in those substances, that chemistry is the art, craft, and business. It always was, and it always will be. But now it's also a science. That's what's changed in the last 200 years. It's a science of microscopic molecules and their transformations. So let me tell you a little bit about that, and along the way tell you a little bit about the scale of these things. So here are some of those molecules. These are, I show them because they're pretty. I show them because they go right into our mind. They are polyhedra of carbon with hydrogens coming out of them, a cube of carbons, a molecule called cubane, dodecahedron at lower left, and at lower right, a molecule C60, a molecule which should be on the flag of Brazil, which has no hydrogens, and which you see here. These molecules are beautifully simple, simply beautiful, and I don't have to tell you that they're beautiful. They have a beeline into our soul. They are immediately beautiful. Now, these are models. These are drawn. The lines are bonds, which is an interesting construction, which I work on. But there are no real bars there. Between those lines, there are electrons, but they're roughly concentrated along those lines, but they're not just in those little bars. But that has become the symbol. So these are symbolic structures, but the scale is that the carbon to carbon distance is of the order of 10 to the minus eighth, 100 millionth of a centimeter between those carbon atoms. And so these are very small. And now the whole story of that, not the whole story, but a large part of the untold story of the transition from substances to molecules that is written down here is that this took place in the 19th century and the beginning of the 20th century, and that we learned something about how the atoms were held together in metric detail, in geometric and in distance detail. We learned this much as we have a map of a continent. We learned this in indirect ways by doing experiments. We didn't just think about it. Experiments were done where measurements, signals from within were used. Light was shined on a molecule. Light came through it. It gave us some information. We learned that there were atoms and that they were arranged in a certain way without seeing a picture. We did not wait for a picture of the molecule. We deduced the arrangement in space indirectly. And that story, which I don't have time to tell you, is intellectually a beautiful, beautiful story. How you can tell something about the innards of a molecule in microscopic detail without seeing it. But of course, you have to do something. You have to do an experiment. Okay, now when I show you these molecules as I told you, they are simple and simply beautiful. One of the interesting things is that these are devilishly hard to make, except for the last one of these, the Buckminster fullerene. Why do I say last one? Because actually these were made in a certain chronological order in the 20th century, from about 1950, 1965 on, over a period of 30 years. And they were made at a certain time by certain people, and Buckminster fullerene was the last one of these to be made. Turns out that the last one to be made is now the easiest to make. And let me translate that. It's the cheapest because it's the easiest to make. The cost reflects the effort in this. This has to do with the business side of paying people to be chemists. Now, I would like the young people in the audience to reflect maybe in their own time about what this means in a general way for your future, that the last molecule to have been made, and you are the people who will make the next molecule, that the last molecule to be made turned out to be the easiest to make in the end. There is something in that that's interesting. But I want to focus on something else. I didn't have to tell you these were beautiful. They were so-called platonic solids. They have an element into our soul. And I feel guilty when I show them to you. The reason I feel guilty is because they have such an easy way into our soul. And I know some other molecules. Here is one that I encountered about 40 years ago with all the atoms in it, about actually a total of about 9,000 atoms, about 5,000 hydrogens, a few thousand carbons, hundreds of oxygens, 12 sulfurs, and 4 irons in it. It looks like a mess. It is not simply beautiful like the tetrahedron, but this is the most beautiful molecule in the world that I know. And I'll tell you in a moment why. Now, first of all, one desperately tries to simplify the representation. Simplify means just to allow it to enter our mind in some format. So one thing one does is one throws away the hydrogens and one throws away the carbon atoms, but connects them up to each other. And you get a picture like this. And now you begin to see the helices of carbon atoms. These are called alpha helices. And there are 4 subunits, 2 red and 2 blue. And then nestled in the arms of these helices is a platelet-shaped molecule that is green. And at the center of that, that's called a heme, is an iron atom. And this molecule, I will not conceal it any longer. This is hemoglobin, the oxygen carrier in our blood, the biochemical molecule we know about more than any other biochemical molecule. If you study biochemistry, you will find 2 chapters in your textbook about this molecule. This, to me, is the most beautiful molecule in the world, and not because it's symmetrical. I had to have someone take me by the hand to appreciate the beauty which is in the function of this molecule, how it carries oxygen, where the oxygen binds, how the atoms change so that if you take one of these platelets and you add oxygen to it, it makes it easier for the other platelets to take up oxygen. There's something called the cooperativity of oxygen uptake. All of these things I had to be taught. And then I could say that this is a beautiful molecule. But there's a lesson there that simplicity is not necessarily beauty, or simplicity is something in our minds. But let me think about that a little bit more. Let me first tell you that most of the molecules of chemistry, and chemists have made in 200 years of frenetic activity, they've made about 100 million new molecules. Of those 100 million molecules, very few are beautiful polyhedra. Many are as complex as hemoglobin. Most are of some intermediate complexity. Here is one of these. So it turns out this is a very useful molecule. It's, if you talk to some physician, they'll tell you that this molecule called Taxol, officially paclitaxel, and you don't want to know the systematic name of this molecule. This molecule is an important piece in anti-tumor therapy. It is extremely effective against several tumors. It came originally, was isolated from the bark of a yew tree, which you see here. From the bark of that tree, which took 300 years to grow, they could make, in the beginning, 3 doses of this molecule, which had anti-tumor activity, whose structure you see in 2 representations at right. And this actually tells you something about what will be done next, because to get the bark, the tree had to die. You are not going to make an article of commerce out of something where you have to kill 300-year-old tree to get 3 doses of something. This molecule had to be made more simply. It had to be made, for instance, synthetically in a laboratory. And how do you make something as complex as this? So that is one interesting part of chemistry. I'm talking about a branch of chemistry called synthetic organic chemistry. It's an art and it's a science, and it's wonderfully thoughtful, because you do not make this molecule by throwing carbon and oxygen together and heating it up. It's done by a plan. It's done by a Lego block-like construction from smaller pieces, where you build the 6-membered rings by taking 4 carbons and adding to it 2 carbons, and out comes a 6-membered ring. Very thoughtful construction goes into this. Anyway, I show it here in part to show you the continuity from simple to moderately complex to very complex that represents chemistry on the molecular or atomic scale. Just to remind you where we are in the second look at chemistry. And what's interesting is that I want to stop for a moment on the feeling that made me think that the molecule at left, the cubane, was beautiful and simple, and the molecule at right was complicated and maybe not so simple until I learned about it. So if you move, clearly, it's something about the construction, it's something about the shape. I also hinted to you that chemists build these molecules from simpler structures, just like they build houses, just like they build other structures upscale. In fact, if you move 12 orders of magnitude, 1,000,000,000 times upscale from molecular structures, then you come to structures which are about 100 meters across. And we build such things, and we call that architecture. And what I want to show you, that when human buildings build structures that are 12 orders of magnitude upscale from molecules, that the same struggle goes on in our mind. What struggle? The struggle that goes into saying this is beautiful and this is not. It's what would be called technically an aesthetic judgment. It's a judgment of beauty. So let me show you some examples of architecture where the beauty depends on simplicity. I don't have to go very far because there is a high point of Mughal architecture, the Taj Mahal. And again, I don't need to tell you that this is beautiful. It speaks of itself to us. And it speaks through the element of symmetry, most directly here, and of simplicity in it. Now, if I wanted an example of something else, here I am in a church in Spain. It's Toledo Cathedral. In a period of architecture around 1600 or so, and you see the complexity of every form in there. Nothing is symmetrical as a first approximation. If anything can be made curved, it will be. If anything can be complicated, it will be. There is that opening to the vault beyond, and there are figures strung around that opening, which you see in the illustration at upper right. This is but I don't have to go. I don't have to go that far. I can go somewhere near you to one of the temples at Madurai. And though there is some symmetry in a structure, and I'll come back to that, by and large, the aesthetic element that's at work here is one of complexity, of making things complicated. But actually, even in this, there is played out something which is very important. And that is, let's talk about this. Where does beauty reside? And it goes for molecules or for art. It really doesn't matter, because what's at work here is what the human mind does with the object, whether it's molecular. Notice how many light years we are away from the value of the molecule in terms of commercial value. We're talking about the beauty of the molecule. And that's because that's the way human beings are. they don't really care just about utility. They care also about beauty and emotions. So in fact, beauty resides not in simplicity and not in complete chaos. Neither of those are worthy to be called beautiful. Beauty resides at some tense edge where order and disorder, symmetry and asymmetry are somehow, they're pleasing, but they are struggling with each other. And we subconsciously become sensitive to that struggle. And it's what makes the object interesting. What I show here is a Japanese garden. There's a pond in it. There's a bridge, a symmetrical structure. The person who designed this garden, and to be sure, this Japanese garden and the bridges in it that you see one in the background too, these are objects of human creation. They were designed for a purpose, to be beautiful. And you can be sure that when the person chose to put plants at either end of this bridge, that most certainly, if they had any sense in their head, they would not make the plants identical. The plants on one side of the bridge are different from the plants on the other side of the bridge. Given that the bridge is symmetrical, what you do is you introduce an element of tension in there in order to make it come to life. That is what life is about. Order sets a foundation, disorder sets a tension, it actually confers life. There is so much more that one could say about this. Okay, now I come to the third way of looking at molecules, and this is, we looked at substances and their transformation. Macroscopic, we looked at microscopic, just a sketch. And I think you will understand that this is not the usual way that people look at chemistry, but it's useful sometimes to look at different ways. The third way has to do with psychology and emotions. I've already hinted at this in a number of ways, that there are ways that people think about chemistry that come from what chemistry is, and I'm interested in how they think about it. So one of them I already told you about, which is implicit in this comic book from 80 years ago, and that is that chemists are the ones who do dangerous explosions, and all the complexity that the explosions are not. The explosions are what chemistry is, but the explosions are not what chemistry wants in order to be a profitable business. What I just showed you, that tension around the explosion, is also part of a kind of it's one of a sample of dualities that can characterize any chemical, any molecule, and that are in our minds not all at the same time, but they can be at the same time. And when they are in our minds, they in some way create a tension and therefore create life or interest in the molecule. Here is an obvious one: harm and benefit. So here is morphine, which is a product from a poppy, a chemical known for its pharmaceutical uses in various folk medicines in the world, found that way. And anyone who is listening to this talk who has had a major operation will know what morphine is good for. It is the first line analgesic that is given for the most severe kind of pain, such as that, for instance, in the stages of the operation. And it is also what the doctors will try to get you off as soon as possible because it is addictive. And that morphine, the structure of the morphine is at right, and this is a way of writing out the chemical structure. I just show it here to show you that it is a molecule of small to moderate complexity, a little less complex than Taxol. This can be made synthetically, but it's also made from a natural product from poppies. The morphine, and also the second thing is about morphine is that a derivative of it is a still more deadly and only addictive substance, and that is heroin. So what the point I want to make is that it's not two different molecules that are analgesic and addictive. It's one and the same molecule. And that's what's interesting, that that molecule has a harm and benefit side. The same thing about other things you've heard about, like ozone. You heard about what we've done to help save the ozone layer in the atmosphere, which protects us from ultraviolet radiation. Well, that same ozone at sea level causes photochemical smog and damages lungs and tires. So ozone, it's not any different molecule, it's the same molecule. That harm benefit and that balance makes something interesting. Makes something interesting about the molecule. And let me go on, let's see if I have another one. It gives this two-faced image of molecules and of chemistry that some of my colleagues are very unhappy with. They think that the press just encourages the harmful side, but I think the press is what the press was. Good news is no news, and bad news is good news. So with the press does what it does. It's up to us to show both the harm and the benefit. I don't have the time to tell you many more things, but I've already told you about some of the other kinds of tensions, or actually I have some slides below. Just bear with me for a moment while I skip to them, and then I'll skip back. Yes, here's another tension, natural, unnatural. At left, you see some plants in the allium family, which includes onions and garlic. What would the world be like without plants in that family? Tasteless. They are wonderful. At right, you see something which is clearly unnatural. Okay, so that sets up the tension. That sets up a difference which makes you think that somehow you could avoid the thing on the right and still have the thing on the left. But you have to think a little bit more deeply about this. 1 or 2 garlic plants are natural. A field of garlic is not natural. It's agriculture. Agriculture is the use by human beings of natural objects for their own benefit. You can argue about whether agriculture is good for you. Of course it is good for you. We would not have as many human beings alive if it were not for agriculture. You can argue about whether you should use fertilizers or not. But the point I want to make is that the natural unnatural divide is not as simple as contrasting a factory with a field with some onion plants. It is rather, it's a much more interesting balance between a field of garlic and a single wild garlic plant. I now want to go back, actually, excuse me for the digression. I have shown to you a number of different dualities or polarities which you can ask of a single molecule or of a group of molecules. For instance, we've talked about simple and complex, like cubane and hemoglobin. We've talked about macro and micro, the substance in real gram quantities and the substance microscopically. We've talked about symmetry and asymmetry, about harm and benefit. And now I wanted to show you natural, unnatural. There are other polarities. Static dynamic. Are the molecules, the pictures of the molecules I showed you are all static. You know those molecules are not static. We know that those molecules are in constant motion, the atoms vibrating and sometimes moving more drastically. There are others, we've talked a little bit about, not too much about pure and impure. There are other tensions, to reveal or to conceal. What am I talking about when I say to reveal, to conceal? I'm talking about when you find a chemist, a molecule, a new way, let's say something useful, like finding a new polymer that is biodegradable. Do you patent it or do you publish it? That's what I mean. There are interesting tensions there. There is a tension around trust and skepticism. When someone reports in a paper in the literature that they found something, how do you trust them? How do we trust that there is global warming? These are tensions within science. Okay, so what I want to tell you is, and this influences how we think about molecules, that every chemical compound, every molecule gains interest because it is balanced dynamically along each of these dualities. And you can ask those questions. You can ask those questions of the molecule. So that makes the molecules, I think this makes chemistry interesting, and not just the chemists. Once people start thinking about harm and benefit and them being implicit in the same molecule, it makes things much, much more interesting to think about. It also leads you to think about other things. For instance, go back to the beginning, and I told you that chemistry is about A plus B going to C plus D. It is about change. It is fundamentally and basically about change. And now I want you to think about the fact, how will people think about chemistry? And that's going to be affected to some degree by how normal people think about change. A plus B going to C plus D. How do you think about change in yourself, in your country, in the political party that governs your country? The nature of thinking about change in human beings is actually ambivalent. We want change and we don't want it. And that's very interesting because it makes it clear to me that a science so fundamentally about change as chemistry is, will not be seen in simple ways by society because it is an emblem of change, because it is so fundamentally about change. All right, maybe that is enough of the story as I've told you. I hope that now I have justified to you, first of all, that I've given you three views of very different views than you normally see of chemistry. I've said three views of a science and culture. I hope that by placing the questions about the beauty of molecules in the cultural context of what we consider beautiful in architecture, or in showing you how chemicals are actually used to produce cultural objects that flash by in one slide in those first pigments. I've shown you something about culture. The chemistry's essential tensions. I may be a little strange in seeing the tensions, but to me, tensions are creative. Tensions are good. Tensions are a sign of life. And so to me, these tensions that I see in chemistry, these dualities, are what makes chemistry interesting. Thank you very much for allowing me to tell you this story. I'll be glad to answer any questions.
Thank you for the delightful lecture. Since you have placed the art of synthetic chemistry in a viewpoint of dualities, and now as a practicing chemist, I am reminded of another duality that actually controls the practice of the science, the duality of a utilitarian approach versus a curiosity-driven approach. So we can look at the science as a quest for knowledge or curiosity-driven human activity. And at the same time, there can be another viewpoint that why should we spend all the resources just for curiosity, unless you have a very well-defined use for it. So yes. Utilitarian versus quest for knowledge. So that duality is also operative, isn't it, in this whole practice of science?
Yes, it is. And the governments of this world continually remind us of, under different names, of the importance of the utility. And we ourselves, when we seek the approbation of the public, we talk about pharmaceuticals and that cure things. We talk about things that make everyday life possible and comfortable for us. So we talk about utility. I myself go through phases where I am primarily driven, of course, by the search for knowledge, by enlargement of what we know, of ways of thinking about things, and by teaching, which is waking up in young people the ability to think that is inherent in them already. I don't teach them facts. The facts are boring. The facts they can learn elsewhere. I teach them how to use their mind in some ways to think. And I go through that, and I'm happy, as most people are in that. But then I feel guilty that I'm not doing my share to make a new pharmaceutical. And then I'm made happy again when I think that the kind of considerations that Woodward and I did about organic reactions, I don't own a single patent. So that is the prima facie evidence of how useless I am. My name is not on a single patent, but yet There are hundreds to thousands of patents that use concerted reactions to construct molecules that are useful. And I am very happy. I don't want any rewards from that. I'm perfectly happy. But my society has enabled me to do that. I know I am privileged. I think there must be a place always for enlarging knowledge. And the European invention of the university created that situation. It's something to admire. It's precarious. It's subject to political action sometimes and to control. I somehow think we must find that any society, any subsection of our society, that any country, any province has to find a way to support both. It is attention.
Since you have pursued your career on topology-based research in pericyclic reaction, so can you, with your insight, in which topology does our universe exist? Huckel topology or Mobius topology, or a dynamic equilibrium of both?
So the world we move in is three-dimensional Euclidean. The astrophysicists need to move into other dimensions when they deal with objects that are 10 billion years old and the history of the universe. The amazing thing is that the human mind, even in this three-dimensional world, can conceive of higher dimensions and can prove things mathematically about what can happen in higher dimensions or in other topologies. It took some time to get to a Möbius topology, but it was eventually found. But we can conceive of things. I'll give you a specific example because it's good to have a specific example about how good human beings can be at conceiving the impossible in our world. As you know, you can pave your bathroom floor with squares and with triangles, equilateral triangles, and with perfect hexagons. You can't pave your bathroom floor with perfect pentagons. You get little nooks and crannies left over of angle. But if you go outside of 2 dimensions, which is what your bathroom floor is, you can create a 3-dimensional object, which is a dodecahedron, which is made up of perfect pentagons. Going in another dimension, it is impossible to fill 3-dimensional space with perfect tetrahedra. It looks like it should be possible. Tetrahedra are so beautiful, but you start stacking tetrahedra, and I'd urge students to do this, and you find that just like in trying to pave your bathroom floor with pentagons, you cannot fill 3D space with tetrahedra. There are little crannies of angle left over. It turns out that in 4 dimensions, you can create a polyhedron, which is all made out of perfect tetrahedra fitting together. And in 8 dimensions, you can fill all of space with 8-dimensional tetrahedra, equivalent of tetrahedra. It's impossible for me even to imagine that in terms of things. I can do 4 dimensions by projecting into 3, but 8 I cannot do. It's a mathematical structure. I can see how the theorem was proved, but I at this point I lapse into into wonder at the mathematician who can conceive that idea, and that's wonderful.
Thank you. Thank you.
Yes,
Hello,
there was one comment in the chat that I had a false concept that symmetry leads to beauty. The concept is not false. The concept rather can be rephrased. We have biologically built into us a favoring of symmetry, which makes us think that symmetrical objects are the criterion of beauty. They are one criterion of beauty. And so I think we are more than our biology. We demonstrate that in a number of ways, and one of the ways we have gone past that simple prejudice built into our minds is that we can learn how to admire asymmetry in various ways and to value it, but you need to be taken there. You need to be helped along. Now, as another question that says, Professor Hoffman, there are people having this criticism that chemistry is focused to details, intricacies, and is missing the aspects of seeing the big picture or pattern of things. Well, what is your view on this? Yes, but that's in the nature of the educational process. First of all, that the focus is on small things, and the purpose of my lecture is to get you to think about the bigger things, at least part of the time. The more generally, there is in the education, one gains strength by becoming an expert about a small part of this world. And then there's a problem. You can get stuck there. You can stuck there that you can't see the forest for the trees is one way of saying it, but you can get stuck in that small. So what you need is someone or something to ask you to look at the bigger picture of things. I know for myself that I did not start giving general lectures of the type that you have just heard until one time when I was asked to give some lectures at Yale University. And as part of the lecture series, it was some named lecture series. And I had to give, the lecture series was specified as giving 2 technical lectures and 1 general one. And they actually defined the general one in just the terms that you have. That is missing the big picture or the pattern of things. So I'm a good boy. Someone asks me to do it, I do it. I created a general lecture because someone asked me to. And so that was the beginning. And I found that the general lecture had a good reaction to it. So the moral behind this is to do the same thing to other people. If you invite a lecturer for a week, ask them to give a general lecture. So something you should not do is to ask them to talk about the future, because that really is hard to do. But ask them to reflect on what they have done and or on some aspect of what they have done. And if they find out that it's not been published, and if they have a sense of the audience that it doesn't need to be published, that what they say is not on paper, they'll actually feel easier and better to say it. So you get some very interesting things that way. There is a question about, to talk about the smell of compounds, esters. These are not considered under study in chemistry, which might be explained from subatomic particle views. I don't know too much about the sense of smell. It's rather complicated and very important because it goes into, feeds into the sense of taste as well. What I found interesting was that I saw somewhere a paper that focused on, in talking about the sense of smell of something, focused not on the shape of the molecule and our usual considerations in terms of the action of small molecules on biological receptors is that they somehow fit into a certain receptor and then nerve signals are fired. But this one this was a paper that talked not about the smell being determined by the shape of the molecule, but by its vibrations. So the vibrations have a certain characteristic frequency, which chemists actually use to identify a molecule. And this paper, I've now forgotten the author, I'm sorry, talked about characteristic vibrational frequencies of the molecule determining how it smelled. And that was interesting. That was a different focus. Yes, there is another question. I'm curious about your thoughts about machine learning compared to the future of traditional DFT. So this is actually something on which I have some complicated and strong feelings. Let me just say that I and a French theoretical chemist, Jean-Paul Malrieux, have published last year a series of 3 essays in a leading chemical journal, Angewandte Chemie, called, the title of the papers is Simulation versus Understanding, a tension, and not only in our profession. So this is about the wave of machine learning or artificial intelligence in general that is breaking over our heads. And there is nothing wrong. I cannot summarize the whole lecture series, but I'm very worried when the claims are made that the machine learning, or as enabled perhaps in the near future by quantum computers, that this will, when claims are made that this will provide a better understanding of chemistry. And I think there is no sign in what we have so far. What we have is that those technologies will enable better numbers, better agreement with experiment on observables for specific numbers, for specific molecules. If you ask what are the characteristic vibrational frequencies of Taxol, the quantum computer will give them to you exactly, better than experiment. And then you ask the computer, what happens if I replace a oxygen by a sulfur in the molecule? And it'll say, I have to go back and calculate. And it gives that number exactly. And it answers that to every question, to every modification that you make. I would say that molecule does not understand, that computer does not understand that molecule. It is a perfect simulation device that solves Schrodinger's equation exactly. But then so does the molecule. There's still tremendous utility because the computer can provide observables which are not observable, which are difficult to measure. But understanding? I have a simple definition of understanding. Understanding is what I can teach, what I can tell a student or an expert in the field. I may have to use a computer. I may have to use some complex tools, but it's something that I can communicate. And what I'm worried, I'll put it using philosophical language, is when epistemological claims are made about machine learning and neural networks and quantum computers. Meaning epistemological claim just means that they understand. I would say they understand nothing. It's human beings who understand, who can teach other human beings. Now, there is a branch of artificial intelligence that has to do with explainable AI. That's when you focus on having the artificial intelligence apparatus of deep learning or machine concentrate on producing explanations that are in human language. That's interesting. And I'm keeping an eye out on that. There's much more to say about this, but I would urge you to read our 3 essays in Angewandte Chemie. Yes.
So do you have any advice to our researchers?
Yes. So first of all, that's Professor Woodward and I had, of course, wrote that paper together. The whole story of doing that work is being told in a sequence of 20 papers by Jeff Seaman, which will be a book. It's the story of the orbital symmetry, a story, and it's also a story of physical organic chemistry in that period. That sentence, I resisted. I did not want to put in. Woodward insisted on it. And he said, first of all, it's generally right. And second, if you put a sentence like this, given the nature of human beings, it'll stimulate human beings to find exceptions. That is, human beings rise to challenges. And and he was absolutely right. Now, why did I resist it? I resisted it because I could see that if you make the components in a cycloaddition, to be very specific, let's say a 2+2 cycloaddition, if you make the components very asymmetrical, so that you're adding a BH bond to a CN double bond or something like that, that the asymmetry will be such that it no longer, that the transition state will be highly asymmetric and it'll lose that forbidden character in it. And so I thought, why put that in when it is a limitation? And he said, no. Okay, now the other part of the story is he was 47 years old at the height of his powers, and I was 26 years old and a young person. And of course, I followed his advice. Wouldn't dream of not doing it. The second part of the story, though, is interesting, which is part of what will be traced, is how did a pair of helping hands turn into a collaboration? Or to put it another way, in the 5 Woodward and Hoffmann papers of 1965, the first is Woodward and Hoffmann, and the second one is Hoffman and Woodward. And when that came out, everyone sat up. And so Professor Woodward had the insight to create a collaboration out of that. But still, on that particular point, he also had a high writing style. Some of you will know my writing style, and I have a style too. And I'm a strong believer in style within science, where all the gatekeepers conspire to keep style out. The referees and the editors. But still there is I have a style in the way I use the drawings. I have a style in the way I use the arguments in the paper. I have a style. My style is not Woodward's. Woodward's was a high 19th century writing style. You can look and see it in his papers, his synthetic papers. That high style carried through in the orbital symmetry long paper. I was not yet in control of the style, so to say, nor was I that much in control. I'm not trying to get out of that sentence. I'm actually giving you a bit of history. So yes, it's a good sentence and psychologically well designed.
There is a question from one of our faculty, Aniditi. Can you please tell us about the framing of pericyclic reaction, Woodward-Hoffmann rule, and how long it took for the framing?
You will see only one of the 20 papers by Jeffrey Seaman has been published in Journal Organic Chemistry a few years ago. There'll be 20 papers which trace the development. Very fortunately, in that period, I kept careful scientific notebooks. I don't do that any longer, but we have a good case for tracing the things. It took a period of it was a development with scrambling to get more understanding in stages. It took only a year from when we started the calculations to when I think maybe a year and 3 months still from the time I started the calculations, which enabled the construction of the qualitative thinking, a year and a half until the sigmatropic reaction paper was published. But even then, things did not develop for another 2 years. Let me give you an example. Nothing goes very straight. We did not see that all of these reactions, electrocyclic, cycloaddition, and sigmatropic, even just the fact that we gave them different names, is evidence that we thought they were different reactions. We did not see that all were cycloadditions or could be seen as pericyclic reactions, as cycloadditions involving pi and sigma bonds. The idea of seeing sigma bonds as components in a cycloaddition took us a year to get to. Other things about stereochemistry, nothing was very straight. For instance, in the initial paper on cycloadditions, we only imagined cycloadditions in which the addition took place on the same side of the pi system, what are now called suprafacial additions. And it wasn't until about 2 years that we saw that you could imagine cycloadditions which took place on opposite sides of the pi system. In between, after 1 year, we came up with sigmatropic reactions where a hydrogen could shift from the top face of a pi system to the bottom face of a pi system. But we were not smart enough to see that that could be done for a pi system interacting with a pi system. So the world always seems simple and logical in retrospect, the reality of getting to understanding is an involuted task where the people who gain the understanding never quite have complete control of what they have found, but slowly they get a better understanding. So I think by the time we wrote the long paper, which was 4 years after we had done the initial work, we really had almost all the picture in place. Yes, so you'll learn a little more about the history from the Seaman papers. So maybe I think we have come to the close of the questions. People should feel free to write to me. I have a website with my email on there. It's easily accessible, and I'll be glad to hear of people, from people. I'm very glad to speak to students in Kerala. I have been only once in your beautiful region, and it was a great pleasure.